Hello everyone. In this session, we will be discussing regarding the third module, that is Maxwell's equations and electromagnetic waves of the engineering physics paper. Now, in this chapter, we will be discussing regarding the basics of the Maxwell's equations and the basics of the electromagnetic waves. So, in order to discuss Maxwell's equations, we have to start with what is called as scalar as well as vector quantities. Now, if we consider the physical quantities, the physical quantities can be broadly classified into two types. Those two types are, first one is scalar quantity and second one is vector quantity. Now, what is meant by scalar quantity and what is meant by vector quantities? We will go with the first one, that is scalar quantity. Physical quantities which has only magnitude but they do not have any particular direction, such kind of physical quantities we call it as scalar quantities. A physical quantity which has magnitude but does not have direction is called a scalar quantity. So, if you consider such kind of scalar quantities, although scalar quantities will be having only the magnitude, or else we can say we can define those scalar quantities by only its magnitude, it will not be having any direction. The example of scalar quantities are temperature, heat, mass, etc. So, likewise, there are various examples for the scalar quantity. Some of the examples are temperature, heat, mass and etc. Now, second one is vector quantity. Now, a physical quantity which has both magnitude and direction, or else a physical quantity which can be defined by both magnitude and direction, such a kind of physical quantity we can call it as a vector quantity. A physical quantity which has both magnitude and direction is called a vector quantity. Now, in the case of vector quantity, all those vector quantities can be defined by its both magnitude as well as directions. For example, we have velocity, acceleration, force, electric field, etc. So, all these physical quantities can be defined by its both magnitude as well as those physical quantities will also be having a particular direction. Basically, a vector can be represented graphically by a straight line with an arrowhead. Here, the length of the straight line indicates the magnitude of the vector and the arrowhead indicates the direction of the vector. Basically, we can represent a vector by an arrow mark on a letter that is vector A can be represented as letter A with an arrow mark on the head. Now, let us say there is another vector of the same length but with an opposite arrow mark. So, we draw another vector of same length. It also has a length of example 0.5 meter, but here the arrow mark is different. The change in the arrow mark does not indicate the vector has a negative value. The change in the arrow mark indicates the vector is in the opposite direction to the initial vector. Next, we will define one of the vectors which is called as a unit vectors. So, what is meant by a unit vector? A vector whose magnitude is unity is called a unit vector. I repeat, a vector whose magnitude is 1 or whose magnitude is unity is called a unit vector. A vector whose magnitude is unity is called a unit vector. A unit vector can be represented by vector A divided by magnitude of A. Vector A is equal to A cap into magnitude of A. Okay. Any vector which is a unit vector can be represented by vector A is equal to A cap into dot product of magnitude of A, or a unit vector A cap is equal to vector A divided by magnitude of A. So, this is regarding how a vector can be graphically represented, how a vector can be mathematically represented, and then the definition of a unit vector. Next is rectangular or orthogonal vectors. Now, if you consider any vector, a vector can be resolved into its orthogonal components or rectangular components. Now, let us draw a figure. Of a cube Let us consider a vector in three-dimensional space. Let us consider a vector from the origin O, okay, and if the vector has to be resolved into its components along Ox, Oy and Oz. So, such kind of a resolution of vector is called as our rectangular components or orthogonal vectors. So, if the vector has to be resolved along the x axis, along the y axis, along the z axis, correspondingly it has magnitude along x axis, it has magnitude along y axis, as well as it has magnitude along z. The unit vectors along x, y and z axis are represented as I cap, comma j cap and k cap. The rectangular system shown in this figure is called as right-handed rectangular component. Now, based on this right-angular rectangular component, the vectors can be resolved along x axis, y axis as well as the z axis. Vector A taken along a vector A taken along x axis can be written as A into I cap or Ax into I cap, where Ax is the magnitude of that vector and I cap is the direction of the vector. If the vector A can be resolved along y axis as well as z axis, then it can be written as along y axis it can be written as Ay into j cap, and along z axis it becomes Az into k cap. Now, if you consider the resolution of components along the Cartesian coordinate system along x axis, along y axis, along the z axis. So, along x axis it becomes Ax into I cap, where Ax is the magnitude and I cap is the direction along the x axis. Similarly, along y axis it becomes Ay into j cap, and similarly along z axis it becomes Az into k cap. Then a complete vector A which has been resolved into its orthogonal components along x axis, y axis as well as z axis can be written as vector Ax is equal to Ax into I cap plus Ay into j cap plus Az into k cap. So, this is how a vector can be written which has been resolved into its orthogonal components. Magnitude of vector A can be written as magnitude A is equal to square root of Ax square plus Ay square plus Az square. So, this is how a vector A can be resolved into its orthogonal components or rectangular components, which are also called as the orthogonal vectors. So, if you have a vector A, then it can be resolved into its rectangular components using the Cartesian coordinate system. Along x it will be the magnitude of vector A, along x it will be x into I cap, along y it will be Ay into j cap, and along z it will be Az into k cap. So, thus we can write vector A is equal to Ax into I cap plus Ay into j cap plus Az into k cap, which gives the direction of the vector, and if you need to find out its magnitude, magnitude A is equal to square root of Ax square plus Ay square plus Az square. So, we will discuss regarding two kinds of products here. One is called as the scalar product of two vectors, or it is also called as dot product of two vectors, and second one is called as the vector product of two vectors, or also called as the cross product of the two vectors. So let us consider two vectors, vector A and vector B starting from the origin O, and let there be an angle between those two vectors. We will call the angle between those two vectors as angle theta. Then if you have to find out the scalar product of the two vectors, then the scalar product can be defined as the product of magnitude of the given two vectors and cosine of the angle between those two vectors. So this is how we can define the scalar product. If we have two vectors, vector A and vector B, originating from the origin O, and there is an inclination of angle theta between those two vectors, then if you have to find out the scalar product of vector A and vector B, then it can be defined as the product of magnitude of the vector A and vector B and cosine of angle between those two vectors. The angle between those two vectors is given by theta, so it is cosine of theta. So we can write the scalar product in the mathematical form as our dot product vector A dot vector B is equal to A dot B cos theta. Now we will see here the properties of a scalar product. The first property is when the two vectors are mutually perpendicular to each other. Theta is equal to 90 degree and cos 90 degree becomes equal to 0. So if you have any two vectors, then if they are mutually perpendicular to each other, then if you take the dot product of those two vectors, the resultant will be equal to 0, because vector A dot vector B is AB cos 90. Since cos 90 is become equal to 0, then the whole answer, the resultant will also become to equal to 0. Hence I comma j cap as well as k cap are mutually perpendicular vector. I cap dot j cap is equal to j cap dot k cap is equal to k cap dot I cap, that is equal to 0. Since all these three are the unit vectors along the component of x axis, y axis as well as the z axis for a particular vector, then if you take the dot product of those vectors, unit vectors, then I cap dot j cap, that is equal to j cap dot k cap, and that is equal to k cap dot I cap is equal to 0. Okay. So this is the first property. Second property is, let us consider if those two vectors are collinear or they are parallel to each other. If vector A and vector B are collinear or parallel to each other, then theta is equal to 0 degree and cos 0 is equal to 1, then we will get vector A dot vector B is equal to AB cos 0, that is equal to A dot B. So, if vector A and vector B are anti-parallel or in opposite direction, to each other, then theta becomes equal to pi and cos pi is equal to minus 1. So, we can write vector A dot vector B is equal to AB cos pi, that is equal to minus A dot B. So, if you consider the two vectors are anti-parallel to each other, they are there in opposite direction, then angle between them becomes equal to pi and cos pi is minus 1. So, we can write vector A dot vector B is equal to AB cos pi, that is equal to minus of A dot B. And the fourth property is, if vector A is equal to vector B, if the both vectors has same magnitude and they are parallel to each other, that is theta is equal to 0, then vector A dot vector B is equal to A dot A cos 0, that is equal to or A square. Then we can write A dot B is equal to A dot A cos 0, that is equal to A square. Then the unit vectors along x axis, y axis, also z axis can be written as I dot I cap, that is equal to j cap dot j cap, that is equal to k cap dot k cap. So, the dot product of all the unit vectors along x axis, y axis and z axis, they will be equal to each other. So, it can be written as I cap dot I cap, that is equal to j cap dot j cap, that is equal to k cap dot k cap. So, this is regarding what is meant by a scalar product or dot product and some of the properties of the scalar product. Now, next kind of product is vector product or cross product. Now, what is mean by a vector product or what is mean by a cross product? Now, let us consider two vectors. Vector A and vector B, and let there be an angle theta between those two vectors, vector A and vector B. Now, if we consider the vector product or cross product of these two vectors, vector A and vector B, which is inclined at an angle theta, is nothing but a resultant vector C, which is a vector quantity where the resultant vector is mutually perpendicular to the both the vectors vector A and vector B. So, vector product or cross product of any two vectors is nothing but a vector quantity, wherein the vector quantity or vector product can be defined as the product of the given two vectors and cos and sine of the angle between those two vectors, where the unit vector is mutually perpendicular to the given two vectors vector A and vector B. a resultant vector whose magnitude is sin theta and the direction is mutually perpendicular to the plane containing vector A and vector B is called a vector product. So, if I consider the vector product of vector A and vector B, the resultant vector is a vector C whose magnitude can be written as AB into sine of angle between those two given vectors vector A and vector B, and whose direction is in mutually perpendicular plane containing the vectors A and vector B. So, this is the plane containing the vectors A and B, and the resultant vector is mutually perpendicular to both the vectors A and vector B, and there is an angle theta between them. So, this kind of product we call it as a cross product or the vector product. So, I repeat, vector A cross vector B is equal to AB sin theta into n cap, where n cap represents the unit vector along the resultant vector C. So, it can be written as vector C is equal to vector A cross vector B is equal to AB sin theta into n cap, where n cap is the unit vector along the resultant vector. Properties of vector product. Vector B cross vector A. Now, usually we take the product of A cross B. Here what happens if we take the product of B cross A? So, B cross A, it becomes minus AB sin theta into n cap, or else it can be written as minus of vector A cross vector B. Now, the second property is vector A cross vector B is equal to, we know that AB sin theta into n cap base into height of parallelogram, or it can be called as area of a parallelogram. So, if we consider the vector product of any two vectors, the resultant vector is the vector C, which becomes base into height of a parallelogram, which can also be called as the area of the parallelogram. Theta is equal to, if the angle between those two given vectors is equal to pi by 2, then vector A cross vector B is equal to AB sin pi by 2 into n cap. Sin pi by 2 is 1. So, AB into I cap cross j cap is equal to k cap, comma j cap cross k cap is equal to I cap, comma k cap cross I cap is equal to j cap. So, we can write I cap cross j cap is k cap, j cap cross k cap is I cap, and k cap cross I cap becomes equal to j cap. So, what if it becomes it rotates in the clockwise direction. then we can write j cap cross I cap is equal to minus k cap, comma k cap cross j cap is equal to minus I cap, comma I cap cross k cap is equal to minus j cap. Okay. So these are the some of the properties of the dot product of the any two vectors. Now next we will define something which is called as a field. So why we need a field? Because we are going to deal further in the case of the gradient, divergence and curl what is called as a scalar field and what we call it as a vector field. Now let us see what is meant by a field, or let us define what is meant by a field. A field is a region in space wherein a function n can be defined at all the points in that space. So that is what we call it as a field. So we define field as a region in the space where a function n can be defined at all points. Now based on this we have to define two kinds of field. One is called as a scalar field and one is called as the vector field. Now we will start with what is meant by a scalar field. A scalar field can be defined as a region in a space in which a scalar quantity is continuous and is defined by a single value at every point of position variable. The position variable can be represented in the form of Cartesian coordinates as x, y, z. I repeat, a region in a space in which a scalar quantity is continuous and it can be defined by a single value at every point in the position variable, then it is called as a scalar quantity. Now if phi is a scalar quantity and the position variable r can be represented by a set of coordinates as x, y, z, then the scalar field phi of r can be written as phi of x, y, z. So this is how we can represent a scalar field. Examples of a scalar field is, one is the variation of temperature at various points in a metal rod, and second is the variation of the electric potential at every point at various points surrounding a charged body. So these are some of the examples of a scalar field. Now it can be defined as a region in a space in which a vector quantity is continuous and is defined by a single value, both its magnitude and direction, at every point of the position variable. So if you consider any vector field, or if you consider a field to be a vector field, then a vector quantity should be continuous and it should be defined at every by a single value of both magnitude and direction at every point in the given position variable. So such kind of field is called as the vector field. Now if we consider a V is a vector field and the position variable is r with a set of coordinate as x, y, z, then it can be written as a vector V of r is equal to V of x, y, z.